Let's talk about systems of linear equations. If you have had a lecture basic mathematics, then most likely you will know Gauss elimination. What is Gauss elimination? If you have, for example, 3 equations in 3 unknowns, then you have a technique, and this technique is able to find the solution of the equations. Let me illustrate that on paper. If we talk about this system, what do? The first we can do, we eliminate the variables, but that is only for convenience. But when we later implement in MATLAB, then obviously we will only deal with these numbers. And so let's get rid of the variables. But we get rid only in the notation. Apart from that, we know there are the variables. Okay, and now what's the technique? I want to get here a 0, here a 0, and here a 0. That's what we want to have. So let's number the equations. First, we copy the first equation. Okay, and now we take the second equation and we modify this second equation by adding some multiple of the first equation, and we choose the multiple such that we get a 0 here. So this line plus a multiple of that line, which multiple do we need to get a 0? And this is obviously a -2. So we get a new equation 4 by taking the second equation and then adding the -2 fold of the first equation. And then we get this equation. So the job is done for the second line. Let's do the job for the third line. We take the third equation and we add a multiple of one of these equations, but we always take the first equation to kill the elements here. So which multiple of the first line do we have to add to the third line to get a 0 here? That's what we want. So we need the -3. We take the third line and we add the -3 fold of the first line, and if we do so, we get that 0. -3 times that plus here is a 8, -3 times that plus here is a -6, and -3 times that plus that is a 20. Now we have a new block consisting of 3 equations, and these 3 equations are equivalent. And that means that we can forget about these equations and instead work with these equations. So this is the reason why we copied the first line. Okay, now the job is kill the 8. But first, let's copy the first line and the second line. And now let's add a multiple of the second line to the third line to kill the 8. Maybe you say, okay, let's take a multiple of the first line and kill the 8, but by doing that we will get an entry here, and we want to keep this 0. And we can keep this 0 by adding a multiple of this line, because here is a 0. We take the 5th line and we add the 4-fold of the 4th line, and by doing so we get a 0, and this 0 is kept. So 4 times that -2, 4 times that -4. And again, instead of working with these 3 equations, we can work with these 3 equations, and we will always have the same solutions. That's what you can prove mathematically. All the solutions of that block are the solutions of that block, and vice versa. Now we are in that situation, this triangle situation, and having this structure, we know there is exactly one solution of that system. And what are the solutions? Now we take the third line or the 6th line, and let's bring the variable back again so we can better understand. And now we can divide by -2, and then we get x3 is, okay, knowing that x3 has to be 2, then we can use that information in this line. And here we have -2 times x2 plus x3 is -6. We know x3 is 2, and so we can do the following. Let's subtract 2. Let's divide, then we have -2x2 is -8, and then divide by -2, and doing that calculation we get a 4. And so we have x3 is 2 and x2 is 4. And let's use that information in the first line. Let's subtract the 2. Let's add the -4. We can also write it that way. Then we have 3x1 is equal to that. And then x1 is that divided by 3. And in that case we get, and so this is the solution. So let's go back to the script, and the process here is called back substitution. So the process getting out of that equation x3 is 2 and using that x3 here, then we get the information x2 is 4, and then using the information x2 and x3 here, and then getting the solution x1 is 1. This is called back substitution. So, okay, if we understood that logic, we can program that. Let's have some input matrix A. Let's have some input vector B. In our example, A is the matrix 3, -1, 1, 6, -4, 3, 9, 5, -3, and B is 1, -4, 23. And now the algorithm should do the job we did on paper. So what do we do first? Let's find out how many lines do we have in the matrix A, and then let's stick together the coefficient matrix A and the right hand side B. We did the same here on paper. We put 3, -1, 1, 1 together, and we used that line, but forget that line, we don't need it. So this is the matrix C. And now we eliminate in a nested loop. This is the outer loop. This means first use equation 1 to kill in the first column. Then, that's for k is 1. Then, when k is 2, let's use the second line, and then let's kill in the second column. And so go on. In our case, n was 3. So in our case, it was a for loop only for k is 1 and then 2, and then it's finished. Okay, then we do the elimination process, and that means, okay, which line do we update? And here we use K2. K2 starts with line 2, first kill in the second line in the first column, then after doing that, then kill in the third line the first column. And how do we kill? We update the line K2 in the following way. We take a copy of line 2 and then we add a multiple of the first line. And which multiple do we use? We find out which multiple we need. Having here a 6 and having here a 3, how do we find the factor? We have to divide 6 divided by 3, and this is that division. And then let's use a minus. So in our case, it's 6 divided by 3 and a minus, that is -2. And so we get this number. And so we take the second line and a multiple of the first line, the twofold of the first line, and doing so, it's guaranteed that we get a 0. Then K2 is 3, and then we produce that line. We take the third line And then we add a multiple of the first line, and we take which multiple? We divide 9 by 3, and this is this. And then we take that multiple of the first line and add it to the third line. That is this. We take the third line. We found 9 divided by 3 is 3. And so we take the threefold of the first line minus the threefold, and then we get this line. Then this loop is over, and we step here to k is 2. That means now we will take that line and kill in all the lines below, and then we do that loop again. Here k is 2, and k2 starts with 3. So we copy these two lines, we don't have to do anything, and then we update this third line by doing what? We take this third line and then we add a multiple of that line such that we get a 0. How do we know which factor do we have to use? We divide 8 divided by minus 2, and that's what's going on here. And then the nested loop is over, and then we can call the back substitution process. We program it in a new function because we later use back substitution again, and we don't want to have the logic here in Gauss simple, so we use an external function, and this function is here. First, let's find out how many lines do we have in our R matrix. R is, in our case, the matrix 3 minus 1, 1, 0, minus 2, 1, 0, 0, minus 2. I show you that. This here, the left part, this is the R matrix, and the B is 1, minus 6, minus 4. That's how back substitution is called here. Okay, let's start with an initial x, and then we fill the entries of x, starting with the last one, and then going up to the second to the last, and so on. So now this is a very interesting line, and if you are not familiar with MATLAB, maybe this will not be so easy for you to understand. Okay, I will show you in detail on paper what goes on here. Okay, so what happens if R is that matrix? Okay, this matrix is R, and this is the B vector. So, okay, let's start. K is 3, and then x3 is b3, what means minus 4, minus, and then, very interesting part, now let's do the following. Let's take the third line and the entry starting from 4 to 3. And here we have x starting from 4 to 3, and then we divide that by R3, 3. What will happen? This is empty. Starting from 4 and going till we reach 3, that is nothing. So this is empty. This is also empty. Empty matrix times empty matrix is an empty matrix, or maybe a 0. So 0 divided by something is 0. So we have, and one parenthesis is missing, it's that parenthesis. And so we have minus 4 minus 0 divided by minus 2, and this is 2. So this is the most hard part of that program to understand, okay? Now we step k, but step it from 3 by minus 1, so 2. So now we get x2 is b2 minus 6, minus now R2 3 to 3 times X 3 to 3 divided by R2 2. And this is minus 6 minus 1 times 2 divided by minus 2. And so we have this minus 6 minus 2 divided by minus 2, and this is plus 4. Now we step k from 2 to 1, and x1 is b1, b1 is 1, minus r1 2 to 3 times x 2 to 3 divided by r1 1. This is this part. This is x2 4 and x3 2 divided by 3. This is matrix multiplication. Minus 4 plus 2 is minus 2. And so we get 3 divided by 3, what is 1. And this is exactly this operation. 1 minus 4, this comes from here, plus 2, this comes from here, and then divided by 3, and we get that 1. And so we understood that part of the code. Now we have a clear understanding of that code. If you don't have me to explain that, then remove some semicolons. Here, this semicolon you can remove, and maybe on top say, okay, this, I put that in the line between 4 and that without a semicolon, so I get the output on the screen. And then again, also let's take that into that line, and then also without a semicolon, then you see what's going on, and then you can understand this process. Okay, and now we can test if we did the programming correct or not, and we can test it first with our matrix 3 by 3, 3 minus 1, 1, 6 minus 4, 3, 9, 5 minus 3, and so on. We can test it, and then we can see everything on my paper is also in a computer or not. And then we see, okay, it works. And then we can also test for very large matrix, very large, 100 by 100. Nobody of us is interested, or there's no fun doing that by hand, but we programmed it by hand, and then the calculations can be done by MATLAB. Okay, let's have this solution x1, some random variables between 0 and 1, also here, and then we calculate the right hand side, and then let's test if the computer will give us this answer or not. Okay, so let's calculate the solution, which has to be that x1. And now let's test if we have x1. But remember, how do we test if they are equal? Never test if they are equal. There are always rounding errors. So take the difference, take the absolute value to get negative values to be positive values, and then check what is the maximal entry, and this should be a very small number, and indeed it's 1.4 times 10 to the minus 12, so it's a number 0.0000000138898, and so we know, okay, our code works as it should. We had 2 examples and they worked well. So very, very nice. If you do that calculation by your own, and I instantly recommend that you do that, please do that. Numerics, it's impossible understanding numerics. You should do that on your own computer. I never understood numerics. I had to do these operations by myself in my octave system and then tried something more than the teacher told me, and then I knew, okay, I got it. Okay, if you do that, then this number will be some different because there were random numbers here, but more or less you will get a similar answer. Okay, and you can also use a 1000 by 1000 matrix. That's horrible, but you can do that. And when I did that, I got this number, so very, very good. The result is very accurate and is more than I would have expected. Runtime, okay, is more than half a second if you ask for a 1000 by 1000 system. Okay. Okay, if you see that this is very convincing and maybe you say, okay, there's no problem, we understood how we can solve systems of linear equations. But that is not true. We can run into trouble we have not seen so far, but we can see, or we will see later, and what's going on. So let's motivate that chapter LU decomposition. If you only exchange the right hand side but keep the matrix A, what does that mean? That means you keep 3 minus 1, 1, 6 minus 4, 3, 9, 5 minus 3, but you don't keep 1 minus 4, 23, exchange these three numbers by some other numbers, then here all the calculations on the left hand side keep exactly the same. The operations, what's going on here, is not influenced by the right hand side. So this process will happen again exactly as a copy, and only on the right hand side there will happen something new. And so it might make sense to first don't care about the right hand side, and then if we did the process on the left hand side, then later it will be easy to exchange the right hand side. Maybe you are not in the situation that the left hand side will keep and the right hand side will be exchanged, but if you are in that situation, then we can take a profit out of the LU decomposition. Okay, but also on top, our algorithm can crash. And when will it crash? Okay, if we have a 0 here instead of the 3, our algorithm will crash because of that division. We divided 6 divided by 3 to find which multiple do we need. And if we have a 0 here instead of the 3, then our algorithm which we programmed will crash. So it's not a good idea to really use our code. So what is a remedy? A remedy, exchange some lines. Okay, that is a remedy. But I will tell you, if it's not a 0, but 0.00001, a lot of zeros, a number very close to 0, then things will get bad also. A 0 will lead to a crash. A close to 0 will lead to a close to crash, and this close to crash is even worse than the crash, because then the MATLAB or Octave will not tell you, okay, I had some problems, but he will produce a solution, and this solution will be horrible. I will show you in later videos. So we have two things which we have to care about, and then that's what we will do in the next section and in the section following. Okay, so this is for the starting of the Gaussian elimination, and we will refine that in the later videos.